I was talking about these projections on various planes. On this figure here, I am drawing the projections of first points B and D on a plane on an E1 E2 plane, and that plane contains the fluid particle A. So I can have several E1 E2 planes. I can have infinite number of E1 E2 planes all parallel to each other. But this particular plane is the one E1 E2 plane which contains the location of or contains fluid particle A at time t plus delta t. This is the phrase I have added. The same slide I showed earlier in the morning, but I have added this phrase to make it clear. And on that plane, I have two angles, delta alpha 3 and delta beta 3. Delta alpha 3 is the angle that AB prime is making, AB prime is making with E1 direction. Okay. And delta beta 3 is the angle that AD prime is making with E2 direction. Okay. Delta alpha 3 is being taken counterclockwise. If somebody is viewing this plane from this side along E3, and delta alpha 3 is counterclockwise, delta beta 3 is clockwise. Then these double primes that I have mentioned here, there are 2 points with double prime superscript, D and E. These are the projections of points D and E, or fluid particles, locations of fluid particles D and E on an E2 E3 plane. Again, there can be infinite number of E2 E3 plane, but I am talking about that E2 E3 plane which at t plus delta t contains the fluid particle A. And on that plane, AD double prime is making an angle delta alpha 1 with the direction being shown here with this arrowhead, and delta beta 1 is the angle that AE double prime is making. A lot of details in this diagram. Taking me time to explain, it would probably take more time for you to grasp it, understand it. You will have to do that. Triple prime. There are 2 points with triple prime superscripts, E triple prime and B triple prime, and they are projections of points B and E, or fluid particles B and E, on an E3 even plane, again which contains this point or the fluid particle A at t plus delta t. On that plane, I have 2 angles marked. AE triple prime is making this angle delta alpha 2, and then the other angle is delta beta 2 that AB triple prime is making. Okay. Why am I marking these angles? I am marking these angles because these angles will help me measure the rate at which various edges are departing from their initial orientation. So at t equals 0, at not 0, at time t, all the edges of the cuboid were perpendicular to each other. I want to measure at what rate they depart from that 90 degrees angle. So these angles will help me measure that. Okay, so these are the quantities we want to have to measure those rates of change in various angles. So the rate at which the projections of AB and AD on a plane parallel to x1, E1, x2, E2 plane tend to align with each other. At what rate this and this, these two line segments are trying to come close to each other, trying to collapse to each other. That is given by what I have here. This angle plus this angle divided by delta t. This is the rate at which they are coming towards each other. The unit of this will be radian per second. Many times we don't even write radian, it will be just per second. Yeah. So this in a way will measure how fast these AB and AD line segments, which were originally at 90 degree, they are trying to move towards each other. Another similar quantity, the rate at which the projections of AD and AE on a plane parallel to x2, E2, x3, E3 plane tend to align with each other is given as this. I'm talking about this angle and this angle. What plane is that? It's a plane which is parallel to x2, E2 and x3, E3 plane. On this plane, these angles are trying to reach towards each other. And finally, I will talk about this plane, the plane parallel to x3, E3 and x1, E1. And on that plane, I want to measure the rate at which these two edges, or rather projections AE triple prime and AB triple prime are moving towards each other, and they will be measured as this delta alpha 2 plus delta beta 2 divided by delta t. This slide I showed in the morning also, I have added a little bit more detail. These things I added to make things more clear. A plane parallel to x1, E1, x2, E2, etc. Again, I have written here to clarify projections. All these projections been shown on a plane parallel to x1, E1, x2, E2 plane and containing FP at t plus delta t. Just made full sentences what plane I am talking about to make it more clear. Again, while I speak, I know this is a lot of information coming your way. You may not be able to completely understand everything now, but when you read the notes, my intention is to put enough information on the slide that when you are ready to read on your own, you will have, you will be able to understand. Okay. So since this morning, I have defined 7 rates of changes with an attempt to describe or quantify the rate of deformation of a fluid element. 3 are here and 4 I defined in the morning. Those 4 things were rate of fractional change in length AB, rate of fractional change in length AD, and rate of fractional change in AE. 3 more. And then I had rate of fractional change in the volume of the fluid element. That was the 4th item in the morning. And then 3 added, total 7 things I have. I want to know, so what is our intention now? So far I have defined the 7 quantities with which I can quantify the rate of deformation. But my attempt is to be able to express these 7 rates of changes in terms of the background velocity field. Okay. I want to find out how much is this or how much is this, how much is this in terms of velocity components or their derivatives, etc. That is what I am going to do now. So the definition is based on physical understanding that these are the things which quantify rates of deformation. but we want to relate it to the background Eulerian velocity field. Now that will require a lot of algebra. For a general 3C, 3D velocity field. So we have a strategy, and this is the strategy almost every textbook follows. To reduce the algebra and make it easier for us to understand the essential derivation process, we first focus on a 2C, 2D velocity field. We find expressions of these rates of changes, rates of deformation of 7 things for a 2C, 2D case, and then subsequently we extend the understanding to a 3C, 3D velocity field. And we will actually sort of extrapolate the expressions from 2C, 2D, and we will write the expressions for the 3C, 3D field directly. Now this is not necessary. If you are willing to deal with all the algebra that it takes to get the expressions in 3C, 3D field directly, nobody is stopping you. You can take like 10 A4 sheets paper, take a pen, spend like 2 hours, maybe 2.5 hours, and you derive everything directly for 3C, 3D. Nobody is stopping. But it is tedious. And that is why people follow this approach, what I'm saying. First 2C, 2D, and then extend that to 3C, 3D field. All right, so rate of deformation of fluid element, 2C, 2D velocity field. That's that much algebra I'm willing to do right now. Same figure at time t, we have this fluid element A, B, C, D, E, F, G, H. The orientations of various faces and edges are the same what I described in the morning. The face A, B, C, D, as you see in this figure, this face is actually parallel to X1, E1. Similarly, this face, this face will be parallel to X3, E3, and so on. So deliberately, we have oriented the cuboid such that its faces are parallel to the native planes of the Cartesian coordinate system. Okay, so I say that the velocity field is 2C, 2D, which means that Vxt will have this form. 2 componential, E3 is gone. So I'm setting V3 to be 0. And 2D. And since it is 2D, I'm just putting x1, x2 here. X3 is not there. It means the velocity field, first of all, V3 is 0. And even V1 and V2, they depend only on x1, x2. There is no change in V1, V2 across various planes as you move along the third direction. Now, since V3 is 0, I hope you will agree that no fluid particle part of this fluid element, no fluid particle which is part of this fluid element will undergo any displacement in the E3 direction. There is no V3. No displacement in E3 direction. One simplification we have achieved. It will reduce algebra. Further, whatever happens to face ABCD, the same thing will happen to face EFGH also. So face ABCD is this. EFGH is this. Both have their normal along E3 direction. This figure, it doesn't look exactly like that, but that's what it is. That's how I'm presenting it. So my claim is that whatever happens to this face, same thing will happen to this face also. Why? Because of this. Whatever happens to the faces V1 and V2 will be responsible for that, and V1 and V2 are not dependent on X3, right? And that is why the fate of the red phase will be same as the fate of the green phase. And thus it is sufficient for me to just pay attention to phase ABCD itself in 2C2D case. Whatever rate of deformation happens to the phase ABCD, that will describe everything. No need to look at the full volume right now. Only one phase will be enough. All right. Now focusing on that phase, I am drawing these two diagrams. So I am taking a break from the three-dimensionality of the problem and focusing only on this phase. At time t, this was a rectangle, and at time t plus delta t, it gets distorted. All the fluid particles move to their some new locations. Now on this figure, I am marking two angles, delta alpha and delta beta. There are only two relevant angles. On the 3D case, I had 6 relevant angles, delta alpha 1, delta beta 1, delta alpha 2, delta beta 2, and so on. Here, only two relevant angles are here. Two relevant angles we have. Again, notice that the way I have drawn the directions of delta alpha and delta beta, one counterclockwise, the other clockwise. Okay. Now, before I start showing you the algebra, I want to show the correspondence that exists between this 2C2D case on the left hand side and the general 3C3D case what I showed earlier. In 3C3D case, I had so many points, single prime, double prime, delta alpha 1, delta alpha 2, all those things were there. Here we have a simplified picture, but let's see the correspondence. What on the right or what points on the right hand side figure become what points on the left hand side figure. So this point B, what you see here, is the fluid particle B itself, and that is lying on E1 E2 plane, on one E1 E2 plane. That point is not only B, but it is also B prime. And the general 3C3D case, what I showed earlier. In 3C3D case, I had so many points, single prime, double prime, delta alpha 1, delta alpha 2, all those things were there. Here we have a simplified picture, but let's see the correspondence. What on the right or what points on the right hand side figure become what points on the left hand side figure. So this point B, what you see here, is the fluid particle B itself, and that is lying on E1 E2 plane, on one E1 E2 plane. That point is not only B, but it is also B prime, simply delta beta here. Okay, I have written these things here. So I have dropped these subscripts. I don't need them in the 2C2D case. I just call it delta alpha, delta beta. And as I said earlier, B triple prime is what I am calling in this background figure as I'm calling this as B prime. It is actually B triple prime in this figure. And what I'm calling as D double prime is actually D prime in this figure. know it could be quite confusing. But again, my hope is when you read it, you will make sense of it. So this is the correspondence part for our understanding. Now let's try to find out what would be the coordinates of B and D and also A and C at time t plus delta t. I want to know the coordinates of these 4 points at time t plus delta t. To find the coordinates of these 4 points, I will need to know the local velocity of these 4 points at time t and the original coordinates of these 4 points. Okay, I talked about it in the morning class also. Get the coordinates of these 4 points. I need the coordinates of these 4 points or FPs and their local velocity. That's what I have written here, again using Taylor series approximation. At time t, coordinates of A, B, C, D and the local velocity components at time t. Let's go to A. Coordinates at time t, x1, x2, base location. At point B, it is x1 plus delta x1, x2. D at time t, x1 plus x2, x1, x2 plus delta x2. And the coordinates of C at time t both have x1 plus delta x1, x2 plus delta x2. So in red color, I am showing the coordinates. In green color on the same slide, I am showing the velocity components. Now here, I am not showing the third coordinate. The third coordinate of every vertex is x3. That's why I am not writing. In this case, the third coordinate is not important. All points have the same coordinate, third coordinate x3, and it will not change. Similarly, V3 is 0 for all points, and that is why when I am writing the components of the velocity vector at various vertices, I am not putting comma 0 like this. If I want, I can put, but it's not required here. Okay. So point A has at time t has velocity components v1, v2, right? Then I go to point B and I write the two velocity components at point B as this and this. Taylor series approximation, first order. Again, since this part is one component of velocity, so both places you have one. This is second velocity component, so both places you have two. But here I have del x1 and delta x1 because point B is displaced. I mean, point B is delta x1 away from point A, the base location. That is why I have to take the derivative with x1 and then multiply by delta x1. Same thing is happening here. Right? Now we go to point D here and I write the velocity components of point D at time t. What is the velocity component? First component of velocity, of course, v1, v1. Second component, v2, v2. But then point D is displaced from point A in E2 direction, and that is why the derivative is with respect to x2. And once the derivative, partial derivative is with respect to x2, that is, this whole thing has to be multiplied by delta x2, Taylor series. I have written the coordinates of C and the velocity components of C also. We will not need it for our derivation, but just for the sake of completion, I have written for these details for C also. So for C, first component of velocity, second component of velocity. Okay. Now, even for the first component of velocity, there are two partial terms, one along x1, the other along x2. Why? Because C is displaced from the base location not only in E1 direction but also in the E2 direction. So you go delta x1 in E1 direction and then you go delta x2 in the E2 direction, then only you reach C. And that is why two partial derivatives are coming here. Same thing goes for the second component of velocity. All right. So once we have understood all the quantities that I have written on this slide, we should be able to find the coordinates of A, B, and D, for that matter even C, at t plus delta t, next time instant. That's what I have on this slide. At time t plus delta t, coordinates of fluid particles A, B, C, and D. Coordinates of A, x1 plus v1 delta t, x2 plus v2 delta t. X1 and x2 were the original coordinates at time t, and then over time delta t, this much displacement has been achieved by fluid particle A. Okay. If you go to point fluid particle B, it had coordinates x1 plus delta x1 and x2. These were the original coordinates of point B, but then fluid particle or point B has also undergone displacement, and that displacement is the local velocity that existed at fluid particle B at time t multiplied by delta t. Yeah. Same idea extended to vertex D, or fluid particle D will give you this, and when it being extended to C, it will give you this. Again, we will not need C coordinates, but for sake of completion, I have written that. Now, the pace at which I am going, I don't expect you to verify everything that I have written. The best way to verify is to go to your hostel room whenever you want to study this subject. Have these notes by your side and derive it yourself. And if there is any discrepancy, any mistake, I would be thankful to you if you point it out for me, and I will then tell other students also. All right. So these coordinates are known now. So today all slides are going to be very busy, cluttered. Lot of material, lot of algebra written on that. And you will have to be more patient with me today than on other days. All right, so what next? I want to find delta alpha. Remember delta alpha, this angle I want to find in terms of the velocity field or its spatial derivatives. I want to find delta alpha because I want to know delta alpha plus delta beta by delta t, right? Rate at which these edges will collapse towards each other. Remember, that would be this. I want to know this. So in terms of v1, v2, v3 or its derivatives, etc. That's what I want to do. So to be able to get this, first let's find delta alpha in terms of these things and maybe the coordinates. Actually, we find delta alpha in terms of coordinates. It will turn out to be, in turn, it will depend on these things. So let's have a look at this part of the slide. Note that an FE is small. This assumption is required to approximate various expressions of the first order term of Taylor series. Yeah, it's just a reminder that all these things what have been obtained on this slide, I am assuming delta x1, delta x2, delta x3 are all small but finite, not tending to 0 but small, such that first order Taylor series is applicable or it gives us some sensible results. Fine. Now tan delta alpha, let's have a look at this figure here. I start with tan delta alpha. Tan delta alpha in this figure will be what? It will be this much divided by this much. That is tan delta alpha. Okay. At time t plus delta t, of course. At time t, there tan delta alpha was 0. So delta alpha becomes non-zero only at t plus delta t. So tan delta alpha is actually this, what I have written here. 2 coordinate. Again, this language is little unusual. 2 coordinate, what I mean by 2 coordinate is the second coordinate of B. Second coordinate of B. If I go back to this slide, second coordinate of B is this. This is the second coordinate of B. Okay. This I would call as the second coordinate, or I am just saying 2 coordinate. This is 2 coordinate of B. And this quantity here I will call as the 1 coordinate of B at time t plus delta t. Right? That's what I'm trying to write here. Tan delta alpha is exactly the 2 coordinate of B minus 2 coordinate of A divided by 1 coordinate of B minus 1 coordinate of A. Trigonometry. We have used this kind of result many times so far, I know. But then delta t is very small. Delta t is also small. Why? Because I will try to find the rate of change of these angles. So I will take delta t towards 0. So it is a small quantity. And thus we expect delta alpha also to be small. After all, delta alpha develops or evolves in time. At time t it was 0, and as time passes it will tend to grow. So if I keep delta t very small, it is reasonable to expect that delta alpha will also be small. And thus I am going to approximate delta alpha by tan as tan delta alpha, right? For small angles, and if we are measuring things in radians, then we know that for small angles, tangent of that angle is almost the same as the angle itself in radians. So delta alpha can be now estimated as tangent of delta alpha using this thing, and whatever coordinates I have assorted so far for various points, I am now going to put them in the expression. So this is what I have written here is the 2 coordinate of B. What I have written here is the 2 coordinate of A at time t. Sorry, time t plus delta t. And this is the 1 coordinate of B at t plus delta t, and this is the 1 coordinate of A at time t plus delta t. The expressions are complicated, they look complicated, but whatever we did on the previous slide, I'm just transplanting those expressions here. And sure enough, things cancel out. Even though we start with a bunch of terms, some of them cancel out. And when things have cancelled out, you get what I have written here. Further, delta x1 also cancels out. And we are left with this measure for delta alpha. What does it depend on? It depends on delta t. Larger the delta t, larger will be delta alpha. That's what we expect. Will deform more. But then it also depends on these spatial derivatives of velocity. And very specific indices are there. In the numerator, you have v2, denominator x1. Here, del v2 del x1, and here you have del v1 del x1. Right? We will keep this in reserve, and then we will come back to this. We will keep this in reserve and then come back to this. Now this has another component, another part, delta beta. So now let's try to find delta beta using the coordinates of various fp's at time t plus delta t. Now delta beta again is expected to be small if delta t is small, and that is why I will approximate delta beta as tangent tan of delta beta. Tan of delta beta. So let's come back here in this figure. I am dropping a perpendicular. Well, that is not important here. That we will use later. Here, delta beta is tangent of delta beta, and then I am writing this tangent of delta beta as this. One coordinate of D minus one coordinate of A divided by 2 of D minus 2 of A. Similar thing what I did here. I am doing that now for delta beta. Okay. Yeah, I've also written here, derive this as on your own. Can be treated as a homework. Then only you will get understand various indices and you will feel hopefully confident that you have understood it. Yes, so continuing with delta beta, 1 of D minus 1 of A divided by 2 of D minus 2 of A. And again, 1 of D, 2 of D, 1 of A, 1 of D, all these things will be borrowed from this slide. Right? This whole thing is 1 of D. This whole thing is 2 of D. This is 1 of A and this is 2 of A at time t plus delta t. Let's pick up these components and plug them here. Few terms cancel out. You get this. Then delta x2 will also cancel out. You get an expression for delta beta. And here you have del v1 del x2 and here del v2 del x2. Not the same what you got for delta alpha. Delta alpha we got V2, 2, 1 here and then 1, 1 here. 2, 1 here and 1, 1 here. Two, 1 and 1, 1. What are we getting here? We are getting 1, 2 and then 2, 2. So they are different. Delta alpha and delta beta are different. So once we have these two expressions for delta alpha and delta beta, now I am going to work on this. We now measure the rate at which the two edges AB and AD are collapsing or moving towards each other. In other words, the departure from their original 90-degree angle. Both are contributing. It's not that AD just remained where it was and only AB was trying to reach AD. Not like that. Both are trying to reach towards each other. Both have tendency to come towards each other, and that's what is captured here by adding delta alpha and delta beta. And note, the sign that I took for delta beta and delta alpha, they are opposite, and that's why I have plus here. This morning I was saying that if one insists, one can put delta beta 2 also. One can use delta beta symbol to show counterclockwise movement. And then in that case, the rate at which the two edges are collapsing for your derivation, we should have not plus here, but minus. That's when you will get the physical quantity, the rate at which two edges collapse towards each other. I'm interested in that. So you would use minus delta beta if you took delta beta to be counterclockwise also. I did not do that. I took delta beta to be clockwise, and that's why the rate at which they collapse must be plus delta beta. Fine. Now this figure, I know it doesn't look neat and clean. We don't need it. That's why I have put this figure here. So now putting delta beta from here and delta alpha from the previous slide, what I got. I put all these things together, divided by delta t, and then delta t going to 0, we get this quantity. Del v2 del x1 plus del v1 del x2. So the mathematical answer to this long sentence that I put here is this. This tells me how fast they are approaching or falling on top of each other. Again, reminder, all these derivatives that are appearing that are at location A, wherever A was at time t. Here, all these derivatives are here at time t where A was. SI unit of this quantity will be per second. If you want, you can put radians also there. You may put, you may not put. But it is per second, no length, no mass involved. There is no question of mass, it's only kinematics. But your length is getting cancelled out. Meters per second by meter. These things are, that's why you get the units as per second. So first thing we have achieved, we have out of those 7 quantities, rate of deformation, first quantity, I have been able to get an expression in terms of velocity field. Now, having found the rate at which the two edges are collapsing each other, now I want to raise this question, what does delta alpha minus delta beta would represent? When it was plus, it definitely represents the rate at which these two edges are approaching towards each other. But what if I make delta alpha minus delta beta? Again, delta beta is clockwise, just the way it was earlier. Same diagram. What will that represent? Now here is a connection between non-rigid behavior and rigid behavior of matter. Had A, B, C, D, E, F, G, H, the fluid element that I have been talking about, same fluid element, had this fluid element A, B, C, D, E, F, G, H been a rigid body like APL 100, d alpha dt must be equal to minus d beta dt. So I'm talking about rate of change in alpha, that small delta alpha, with respect to time and this angle delta beta. They must have been related like that. And you know what? That is what is called the third component of the angular velocity of the rigid body. For a rigid body, rate of change in orientation of any arbitrarily chosen line segment is always the same and is called the angular velocity of body with respect to the reference frame in context. And that quantity is a unique vector for the entire rigid body. So on a rigid body, you take a small solid element, or you take a large solid element, or you take the entire rigid body as one entity. You identify any line segment on that. Every time you measure the rate at which the orientation of that line segment is changing, that will turn out to be the angular velocity. That's what would happen to this case also. Okay. So for a rigid body, this would have given you delta beta would have always been equal to minus delta alpha, rigid body. Delta beta would always be equal to minus delta alpha for a rigid body. Okay. Take a rigid body like this at time t plus delta t, it does this. This is what I'm calling as delta alpha, and this is what I'm calling as delta beta. Clockwise. Rigid body, this will always be holding good. However, for a deformable body in general, the rate of change in orientation of different line segments are different. Thus, strictly speaking, we cannot define a unique angular velocity or rate of rotation for a non-rigid fluid element. You cannot define a unique angular velocity for a non-rigid body. A fluid element is a non-rigid body in general. However, it is customary to define what is called the averaged angular velocity for deformable bodies. Averaged angular velocity. We denote it by this vector. Okay. And omega 3, the way we have drawn these figures, omega 3 means the third component of this vector, average angular velocity, will turn out to be this. What am I doing here? This is the rate at which edge AB is changing its orientation. This is the rate at which AD is changing its orientation. Both are different rates of change. I'm saying I'm going to define an averaged angular velocity. I will add the different rates of rotations of these two line segments, add them and divide by 2. That's why it's called averaged. So I have 3 students in my class. I insist that I want to find the average age of the student in my class. What do? I add the ages of the 3 students, divide by 3. That's what is being done here to define this average angular velocity. Average angular velocity is not the same as the angular velocity because it doesn't exist, but it does give us a sense of how fast a fluid element is rotating, gives a sense of that. It's not strictly the rate of rotation of the body, it's not defined, but it gives us a sense. And that's why in fluid mechanics, we do talk about this quantity also, omega 3. In this case, only the third component I'm talking about. And that will turn out to be the way I have defined it here. It will turn out to be this. Del V2 del X1 minus del V1 del X2 divided by half. How do I get this? The derivation is very simple based on what we have seen already. Here I found limiting value of delta alpha plus delta beta by delta t. I got this. Instead of delta alpha plus delta beta, you put minus sign and rework on this expression. What will you get? Instead of this plus, you will get minus. That's what we are getting on the next slide. So the third component of the average angular velocity is this. Right? So for fluid element, I must use, strictly speaking, the phrase average angular velocity, but clean this before uploading. Maybe I'll do it later. Okay, so we should use this phrase whenever in talking in terms in context of fluids. We should say averaged angular velocity, not angular velocity for fluids. Okay, for that matter, even for deformable solids. All right. Moving on, now I want to find the rate of change in edge lengths of the FE. Rate of change in the edge lengths. Yeah, I'll end the class after this slide. Rate of change in edge lengths of the FE. Right, this was one of the items that I wanted to get an expression for. So 7 items. Okay, don't have it in this set of slides, but in the morning slides I had that. Rate of change in the edge lengths. Actually, we will not find the absolute changes in lengths, but we are interested in the fractional changes. So the rate of fractional change in an edge length of AB, I want to find. What is the fractional change in this? This is at time t, this is at time t plus delta t. This is what I want to find. Len AB, len means length, written here. Length of AB at time t plus delta t minus length of AB at t. So that is the change in length of AB divided by the length of AB at t. So that makes it the change as fractional. What fraction of the original length has changed? Right? And then I put 1 by delta t and the limiting value. This is what I want to find. Okay. Again, I'll use the coordinates at t plus delta t. I am going to drop perpendicular from B to E1 and I let it intersect at point M. On the earlier slide, I called that point as probably B prime. Doesn't matter. On this slide, I'm just calling it M. So BM is perpendicular to E1. We approximate AM as AB times, well, this is not approximation. AM is AB times cosine delta alpha. That is exact, right? AM is AB times cosine delta alpha. But then cosine delta alpha is almost 1 because delta alpha is a small angle. And that's why AM is almost AB. Thus, the length of AB at t plus delta t, which strictly speaking is this length, I am approximating that by this length because cos delta alpha is almost 1. Okay. So this becomes length of AM. What is length of AM? Length of AM is 1 coordinate of B at t plus delta t minus 1 coordinate of A at time t plus delta t. Right? After all, this length will be 1 coordinate of this point minus 1 coordinate of this point. For small angles, this is a good approximation. And then again, the coordinates are known from the previous slide. That's slide number 8. This one. All coordinates are available. I need 1 of B minus 1 of A. I subtract that and subtract that, I get this much. This is the length of AB at time t plus delta t. And thus, this quantity which I want to find, the fractional rate of change, this is the length of AB at time t plus delta t. The length of AB at time t was simply delta x1, right? Divided by delta x1, delta t going to 0. That turns out to be very simple expression, del V1 del x1. Rate of fractional change of length of edge AB. Unit per second. In line with what I am getting here, meter per second by meters, that is per second. And also if you look at this full statement, this is the fractional change, length by length per second. So it has to be only per second, SI units, that's what it is. All right. Again, reminder that all these derivatives, this derivative is at x1, x2, x3, where A was at time t. Okay. Next is the rate of fractional change in length AD. We will do that in the next class. If you want, you can derive it yourself because whatever we did for AB, if you understand that idea, you can implement that for AD also. And you should be able to get the expression in terms of velocities, velocity gradients or velocity derivatives. All right, we'll stop here.